Select the best set of reaction conditions to accomplish the following transformation. So to answer this problem, we want to look at what we are starting with in terms of its functional group and what we're forming. So we should see here that we are starting with an alkene and that the product we are forming is an alcohol. And specifically, we could describe this alcohol as being a primary alcohol. And that's because this carbon atom that the alcohol is on only has bonds to one other carbon, right? So right there, so that's why we would call this a primary alcohol. And so what we want to do is we want to think about the different reaction conditions that we know that can take an alkene and transform it into an alcohol. So we have learned 3 different ways to take an alkene and make an alcohol. Okay, and so the 3 different ways that we have learned is we have learned that we can do an acid catalyzed hydration. So that is essentially using water and a strong acid catalyst. So that's the conditions that are described here in A. So this is acid catalyzed hydration. So that is one way we have learned. We've also learned that we can do an oxymercuration demercuration, a 2-step process. So I'm just abbreviating that just to not spend too much time writing it out. And so those are the conditions that we see here in B. So B is your oxymercuration demercuration conditions. And then finally, we have learned hydroboration oxidation. And those are the conditions that are described in C. So this is the hydroboration oxidation. And so we want to decide between them. And so what distinguishes these is the products that they would form, right? So we want to look at the alcohol that we're forming and decide which of these 3 conditions would be best to give us this primary alcohol. So we want to recognize is that in doing this, we've added water across the alkene. So we can see clearly where we added the OH of water, and where we added the hydrogen was here. So we added the hydrogen to the more substituted carbon of that alkene. So it appears we put the hydrogen on the secondary carbon, and we added the OH to the less substituted carbon atom of the alkene. And so hopefully we can look at this and recognize that this is what we describe as an anti-Markovnikov addition. So Markovnikov's rule, you might recall, described the hydrogen as typically adding to the less substituted carbon atom, and then that whatever functional group you had would end up adding to the more substituted carbon atom. So we see the reverse here, so we call this anti-Markovnikov. So this might be enough for you to recognize that we are going to be doing a hydroboration oxidation in order to get that anti-Markovnikov. So that means that C is the correct answer. And let's just take a quick look at why that is. And this is not a mechanism that we drew the whole thing for, but if we look at least the first step, which is where you add your BH3, we may be able to explain why this is adding anti-Markovnikov. So we have our boron, which is actually the electrophile, and here is the H3. So boron is your electrophile because it's electron deficient. And so the alkene will attack that boron. And so the hydrogen is actually being added as a nucleophile. So that's how we can reverse where it's being added. So the hydrogen is added as the nucleophile. And so what we're going to have after that first step, right, is we're going to have this organoborane, right? So we formed a bond to the boron here, and that's still going to have 2 hydrogens on it and the hydrogen here. So all we really need to know about this mechanism is this is a syn addition they add to the same side, and we still see that stereochemistry carried through to the product. So what happens in your later steps is that boron is replaced exactly where it is with the oxygen. And so that's how we end up with the alcohol being on the less substituted carbon and the hydrogen having been added to the more substituted carbon.